Last time I left you with a problem to do outside of class, and as a first step this morning we'll go over that problem and look at least one more and then move on with hypothesis testing into a different context, a context that's distinguished from the one we're dealing with at the moment in that we will not be dealing with large samples but with small samples. But you will see that the process is very similar. Last time, I think you were left with a situation in which a researcher had hypothesized that the mean marital happiness of people with children, or without children rather, would be greater than the average marital satisfaction of people with children. Yes? And so the research hypothesis was that X bar 1 will be greater than X bar 2, where group 1 is a group of people with no children and group 2 is a group of people with one child. The null hypothesis in this instance we indicated was that X bar 1 will be less than or equal to X bar 2. The critical piece of information to be drawn from this issue is drawn from the research hypothesis. And the critical information is to determine whether the test that you're going to run should be one-tailed or two-tailed. In this instance, is the appropriate test one-tailed or two-tailed? The appropriate test is one-tailed. Because the researcher is hypothesizing not simply that the two groups will differ, but that they will differ in a particular direction. That is, the researcher is predicting positive difference between X bar 1 and X bar 2. So that the researcher is not obligated to test for negative difference between those two groups. So the test should be one-tailed. That is, when we go to the sampling distribution of sample mean differences, this is the negative end of the distribution, this is the positive end. Because we're obligated to test only for positive differences, all of the alpha can be deployed at one end of the distribution. The second piece of information that we required was the level of alpha, which, as I've indicated several times previously, is determined by the researcher. Or, I've added parenthetically, the reader of the research. But certainly in the context of the study itself as it's run, alpha is decided by the researcher, and we decided that alpha was equal to 0.01. We also discovered that sample size was large. There were 108 people in one group and 102 people in the other group. So sample size is large, so that the appropriate test here is a z-test. And that's what we conducted last time, was a z-test. From these two pieces of information, you can derive the critical value of z. That is, how many standard deviations do you have to move above the mean to isolate 0.01 of all of the scores, or 1% of all of the scores? And you do that by using Appendix or Table A, would you agree? Let me ask you, what is the critical value of z?
Is it when you divide 0.01 by 2?
You don't need to divide 0.01 alpha by 2 because it's not two-tailed. So you don't have to deploy half of the alpha value, half of your willingness to commit a type 1 error at each end of the distribution, at each tail of the distribution. We're only testing one tail here, so you can deploy all of your alpha at that tail.
So you just look for 0.01 on a z-value on Table A?
Table A, the answer is sort of. Because Table A is not, the area beyond z is not expressed as proportions. The area beyond z is expressed as percentages. Yeah. So we could, and that's no problem. We simply have to transfer, in order to use Table A, we simply have to transform a 0.01, a proportion or probability, into a percentage. So would you agree that to do that, you simply move the decimal point across two places? We would be looking for a z-score that's associated with an area beyond z of 1%. Why do I get the sense that not everybody did this outside of class? What is the critical z value?
$2.32.
Let me see, 2.32. That would be associated with an area beyond z of 1.02%, which would be the equivalent of establishing alpha equal to 0.00102. Would you agree? This is the problem that arises here, is that when you scan Table A, there is no z-score associated with an area beyond z of precisely 1. And if we're going to simply rely on Table A, then you have to choose between the z-score that's associated with 1.02 and the z-score that's associated with 0.99. The rule of thumb is that the researcher always adopts the more conservative position. That is, adopts the situation in which it is most difficult to reject the null hypothesis. So if we rely on table A rather than some expanded version of table A that fills in all the missing values, we would select as the critical value plus 2.33. Yes.
Where did you find it on the table? Like, what numbers you look under?
Let me just write it down first. Critical value of Z equals plus 2.33. And let me just say, if alpha is 0.01 and you're conducting a Z test, the critical value is always 2.33. If you're testing for positive difference, it will be plus 2.33. If you're testing for negative difference, it will be negative 2.33. Absolutely. See, this is not a matter of having to routinely hunt through table A. All you need are four values. All you need are four values. No, all you need are four values. Those values are knowing whether alpha is 0.01 or 0.05, and whether the test is one or two-tailed. We know that if alpha is 0.05 and the test is two-tailed, the critical value of alpha is plus and minus 1.96. We did that last time. We now know that if alpha is 0.01 and you conduct a two-tailed test, the critical value of alpha is plus or minus 2.33. You simply have to learn the values that are in the two remaining quadrants. And we will do this. This will be so straightforward, you'll say to yourself, my God, thank goodness I have something to talk about my parents with the next time I see them. You'll probably make up some sample questions for them I hope they take you out. I hope you take them out to dinner. Because you're the ones with all the money. So there's yes, I didn't know whether I'd answered the question over here. Yes. Can you press for posterity? That should be our motto in here. Press for posterity.
What I don't get is 0.01 the z-score that we're looking up, because the area beyond z the z-score associated with the area beyond z of 2.33 is not 0.01, so I'm not getting it.
Okay. I think that was the same question here. First of all, you would agree that in order to solve this little riddle, that is, what is the critical value of z, you have to revert to table A. Because what you want to know is how many standard deviations do I have to go away from the mean before I find either Quasimodo or Johnny Depp. I don't know how. I wouldn't want to be around Quasimodo at dinner. But then I probably wouldn't want to be around Johnny Depp at dinner either. Although he's a very good actor. I'm sorry, momentarily I'm going off on a tangent in my own head. You know that the area beyond Z in table A is expressed in percentages. If we express 0.01 as a percentage, it's 1.0%. Is everybody with me? Is there anybody who isn't with me? Is there anybody who isn't with me who wants to be with me? Okay. So you start scanning values on table A, area beyond Z, And the area beyond z, when z is 0, that is in the center of the distribution, is 50%. Yes? And as you move then away from the mean, the area beyond z starts to shrink to 49.6%, 49.2%, and so forth. On the second column of area beyond z, you're still way too high. It's 33.26%. So we move across. The last value on page 337 is 4.55%. We're still way above what we're looking for. We turn the page. Fortunately, we find even more z-scores. You scan down here until you find a value beyond z, a value of an area beyond z of 1.0, and you come to, in the middle of the last column on page 338, you come to 1.02 and 0.99. Yes? That is, you have a choice, because we don't have a complete table of z values. We don't have any z-score of 2.352, 2.3561. Yes? We only have a sampling of values. So you're forced to choose either 1.02 or 0.99. If you choose 1.02, you have changed the value of alpha from 0.01 to 0.0102. And while that may be relatively trivial, what you've done is to make rejecting the null hypothesis slightly easier. Yes? That is, you've increased slightly the likelihood of committing a type 1 error. So that instead of selecting 2.32, you select 2.33, which effectively establishes alpha not at 0.01, but at 0.0099. You've made rejecting the null hypothesis slightly more difficult. You've decreased the likelihood of committing a type 1 error slightly. But given the incompleteness of table A, unless I start to ask you to interpolate between these z values, this is the sort of choice we have to make. But you don't have to make it habitually, because as I've indicated, there are only 4 values in which you have an interest. So if the test is one-tailed, if alpha is 0.01, the critical value of z is plus or minus 2.33. Are there any questions?
Could you go over how we would need to know why it's plus or minus?
It will be plus 2.33 in this instance because the researcher is hypothesizing positive difference. If the researcher were hypothesizing negative difference, that x bar 1 will be less than x bar 2, then the critical value of z would be negative. Because we would be operating down at the negative end of the sampling distribution. Are there any other questions? Yes.
So yesterday, the example we did, the hypothesis was x1 is not equal to x2, therefore it was two-tailed.
Therefore it was two-tailed.
And then today, it's saying,
that x bar 1 is greater than x bar 2.
So that sign is what indicates if it's a
Yes.
one-tailed or two-tailed.
This piece of information, the research hypothesis, is what tells you whether the test should be one-tailed or two-tailed. If the research hypothesis is simply one of difference, then the test should be two-tailed. Because you have to test for positive difference and you have to test for negative difference. So you deploy half of the alpha value at the positive end of the distribution to test for positive differences, and the other half at the negative end to test for negative differences. If, however, the research hypothesis is not simply one of difference, but difference in a specific direction, then the test should be one-tailed. And if the research hypothesis predicts positive difference, the critical value of the test statistic, in this case Z, should be positive. And if the research is predicting negative difference, then the critical value should be negative.
Are we more likely to face problems with one group with one set of standard deviation, mean and weighted mean, or with two groups?
I'm sorry, Senator. I do not recall that conversation. I don't understand the question, and if I've found in the past that if I try to answer questions I don't understand, I often make a fool of myself. So.
Like what I'm saying, like the problems we're going to be getting, like to work out, like on the test, is it going to be with?
This is a test-related question.
I guess so.
Yeah.
Are we likely?
Test-related question. We want to get straight to the bottom line, as you folks say.
Yeah. Are we likely?
I ain't going there.
Oh yeah.
I'm not going there. Whether it's one or two-tailed, whether it's positive or negative difference, is trivial.
Well,
because you can determine those things. They're not difficult decisions. And second, whatever I do on the exam, I'm not going to try and trick you by... There are enough ways to go wrong without me throwing out there deceptive values of a test statistic. This is one half of the process of hypothesis testing. You've now decided the critical value of Z. All you have to do now, or let me say, the second step is to determine the observed value of Z. And you do that by invoking the formula x bar 1 minus x bar 2 divided by the square root of the variance of the first group divided by n1 minus 1 plus the variance of the second group divided by n2 minus 1. And we went over that last time. What is more, you had the same data to work with in this question when computing the observed value of Z that we had in the example we went through in class last time. So let me ask you, what is the observed value of Z? Pardon? Does anybody else say 0.001? What does somebody else say? 2.46. Does anybody say 2.46? You said 3.36? 3.46. Now I've got it right, I think. Did anybody else say 3.46? What did anybody else find?
1.548.
Does anybody else say 1.548? I have no idea, but I'm going to go with the majority. Whatever it was that we worked out last time as the observed value will be the observed value here because I gave you precisely the same data regarding mean marital satisfactions and the standard deviations and so on. So the observed value of Z is 1 plus 1.548. That is the observed difference is somewhere in here. This is the observed value, this is the critical value. Now you've done the second part of the process. There's just one thing left, and that is to evaluate the null hypothesis. On the basis of the data you have here, do you A, reject the null hypothesis, B, fail to reject the null hypothesis, C, throw up your hands and thank whatever gods there are above that no person lives forever? Pardon? There's one brave soul who says you fail to reject the null hypothesis. No, I don't. No. It's a very simple issue. It's a binary choice. You fail to reject or you reject.
Would we turn
If you fail to reject or you reject. I feel like I'm in My Cousin Vinny. If the next words out of your mouth are not guilty or not guilty, you will be in contempt of court. I think I get the picture. No, you don't. You're now in contempt of court. Do you reject the null hypothesis or do you fail to reject the null hypothesis? All those who say you fail to reject the null hypothesis. All those who say you reject the null hypothesis. All those who are falling on their knees and thanking whatever gods there are above that this course doesn't go on forever. If we simplify this, okay, and we say that we round off the observed value of z, and say it's 1.55. What is the likelihood of committing a type 1 error if you reject the null hypothesis? Pardon? How would you answer my question? How would you answer my question? Where would you look? Why don't we try Table A? Because Table A will tell us what proportion of all scores are beyond an observed value of 1.55. So we'll go down to 1.55. It says area beyond Z, 6.06%, which is in proportion terms, is the equivalent of 0.06, what was it? 1.55, 0.0606%. 0.0606. Would you agree? 6.06% is 0.0606 expressed as a proportion. So if we reject the null hypothesis with an observed value of z of, let's say, 1.55, What is the likelihood of committing a type 1 error? Hang on a second, I'm going to get comfortable. Because I think I'm going to take a nap right now. So what do you think? What's the likelihood of committing a type 1 error if you now reject the null hypothesis? There are only a limited number of numbers hanging around here. Take a stab at one of them. 0.0606. The likelihood of committing a type 1 error now is 0.0606. If z is plus 2.33, the likelihood of committing a type 1 error is 0.0099, essentially 0.01. If you reject the null hypothesis on this basis, there is a 6.06% chance that you will be committing a type 1 error. When you established alpha at 0.01, you indicated that you were willing to take a 1% chance of committing a type 1 error. So do you reject the null hypothesis or do you fail to reject the null hypothesis? You fail to reject the null hypothesis because the likelihood of committing a type 1 error, 0.0606, exceeds your willingness to commit a type 1 error, which was 0.01. This, as we'll find out later, is the p-value. If you were to conduct this analysis, or if you were to read of this analysis, the researcher would talk about having conducted a z-test, and the observed value of z was 1.548, and it would say parentheses p, it would probably read greater than 0.06. When p is greater than alpha, you fail to reject the null hypothesis. In order to reject the null hypothesis, and I'm saying the same thing in about 24 different ways, in order to reject the null hypothesis, the observed value of z must be in this shaded range beyond the critical value of z. Anything in this area would be reason to fail to reject the null hypothesis. We would conclude that there is no significant difference between the marital satisfaction of people with children and the marital satisfaction of people without children. Magic. It's magic. You've looked at 210 people here, and you've made a decision not simply about the 210 people, you made a decision about, a conclusion about all people, on the one hand with children, and on the other hand without children. And you've concluded that there is no significant difference in marital satisfaction, the marital satisfaction experienced by those two groups. That is, children appear to make no difference to marital satisfaction, which of course is a lie. Are there any questions?
a little bit confused with like the definition of the null hypothesis connected to the regular hypothesis.
The null hypothesis is simply, and I go not because of the question, but because I know that different people will answer this question in different ways. The null hypothesis, I will say, is everything that the research hypothesis is not. So that when the researcher hypothesizes difference, then the null hypothesis is of no difference. If a researcher predicts positive difference, then the null hypothesis is either negative difference or equality. Negative difference or no difference. And of course, if the researcher predicts negative difference, then the null hypothesis is positive difference or no difference. Let's assume that a researcher hypothesizes that males in an organization earn more than females performing equivalent tasks in the organization. So we have X bar 1, which let's say is the male score, and X bar 2, which is the female score. If the researcher predicts that males in an organization earn more than females in that same organization performing equivalent tasks, what is the predicted relationship between the average income of males and the average income of females? You've got three choices: greater than, equal to, less than. Pardon? Actually, you've got three choices: greater than, different from, less than. Isn't this the predicted relationship between the male score and the female score? The researcher has argued that males in an organization earn significantly more than females performing equivalent tasks in that organization. Yes? Given that, the null hypothesis is that there will be negative difference or no difference between the male and female mean scores. So should the test be one-tailed or two-tailed? And if anybody even thinks two-tailed, I'm going to come in the middle of the night, I'm going to visit you in the middle of the night, and I'm going to put a bat in your wardrobe or your closet. Shower. The test should be one-tailed, yes? The test should be one-tailed because the researcher has not simply argued difference, but difference in a particular direction. So the test is to be one-tailed. Let us suppose that alpha is set at 0.05. What is the critical value of Z? $1.65, did you say? Let's take a, as you say, let's take a shufti. Let's take a gander. 1.65. We go down to 1.65. We find an area beyond Z of 4.95%, which is equivalent to 0.0495. Our only other choice here is 1.64, which would be equivalent to setting alpha equal to 0.505. By the logic that we've been through this morning, we would select the more conservative position, that is, the more conservative value. That is, the value that makes rejecting the null hypothesis more difficult. So we would select the critical value as, in this case, plus 1.65. So you now know 3 of the possible 4 values, critical values of Z, that you will need. Yeah, we've gone through. We want plus and minus 1.96. Plus 2.33 and plus 1.65. Is that right? What would be the, just so we complete this, what would be the critical value of Z if the test were two-tailed and alpha was 0.01? You've got to divide 0.01 in half if it's two-tailed. So you're looking for an area beyond Z of 0.005. Expressed as a percentage, that's 0.5. So you scan down the column C's and you come across 0.51 and 0.49 on page 339. You adopt the more conservative position so that the critical value of Z under that, when the test is two-tailed and alpha is 0.01, is 2.58. Surely you can, all you got to do is fill out this 2 by 2 with 2 values of alpha as the columns and the number of tails in the test as the rows. And then you don't need Appendix A or Table A. Let's march on. Are there any questions about what we've done here in determining the critical value of Z? Because this is 1/3 of the trick. We now need to compute the observed value of Z. And in order to do that, we need to know the average income of the male sample, the standard deviation of the male sample, and the number of males in the what did I do? No, now I've changed that. Oh, God. No. What did I do? Well, you've got half of it. It was fleeting, but I got to say, for me, it was a big part of my life. You know? I'm sorry to see it go, but I will remember it. It will live on in my heart. You know? I don't know how you feel. We need to know the mean income for the males. And let's assume that it's $30,500. We need to know the standard deviation of the male scores. And let us say that is $4,000. And we need to know the number of males in the study. And I hope you do appreciate the difficulty of being left-handed. This whole thing would be reversed if I were designing these things to be reversed. Let's assume that there are 100 males involved in the study. Large sample. We also need to know the average income of the female sample. And let us presume that the average income of the female sample is $25,000. Let us assume that the standard deviation of the female scores, income scores, is $2,800. And let's assume that there are 100 females in the study too. We now invoke the formula for Z, which is X bar. I'm so afraid of touching something else. It's like riding in air, free fall. X bar 1 minus X bar 2 divided by the square root of S1 squared divided by N1 minus 1 plus the variance of S2, that is S2 squared divided by N2 minus 1. And we can now plug and chug here, you would agree. This equals X bar 1 minus X bar 2, would you agree, is $5,500. It's $30,500 minus $25,000 divided by the square root of S1 squared. S1 is 4,000. 4,000 squared is some really big number. Divided by N1 minus 1, which is 99, plus S2 squared, which is 2,800 squared, divided by 99, which is another big number. And that equals an even bigger number. Right. And if you take the, then you've got to take the square root of that huge number. And you find it's a pretty big number still. I get, let's say, it's 4,009.9. Let's say 4,010. If you divide 4,010 by 55, or divide 5,500 by 4,010, I think you get 1.37. This is the observed value of Z. It's not important if you get the wrong answer when you plug and chug. That's relatively trivial at this point. What's important at this point, much more important, is you understand the process. We'll get the plugging and the chugging of the numbers by just doing it repetitively. But at this point you should understand and have accomplished two things. One is determination of the critical value of Z. And in order to do that, you need two pieces of information. You need to know the research hypothesis to determine whether the test should be one or two-tailed, and you need the level of alpha. You then need to be able to compute the observed value of Z, and you do that by invoking the formula of x bar 1 minus x bar 2 divided by y divided by the square root of whatever it is. And we've done that. There's only one thing left to do, and that is to evaluate the null hypothesis. Given the evidence that you have, would you A, fail to reject the null hypothesis, or B, reject the null hypothesis? All those who say you would fail to reject the null hypothesis. All those who say you would reject the null hypothesis. All those who say, I just don't know. The critical value of Z was 2.58, is that right? Or 2.33? 1.65. That's right. I was thinking the test was of a different kind entirely. This represents alpha. If we go back to the sampling distribution of sample mean differences, establishing the critical value of Z, that is translating alpha into a Z language, says that the critical value of Z is plus 1.65, because beyond that value reside 0.01 of all scores in this sampling distribution of mean sample differences, sample mean differences. I go back. You're looking for the weird. You're looking for the weird. You're looking for the deviant. By that logic, and by the logic of establishing this as the critical value of Z, that is alpha equal to 0.01 and a 0.05 and a one-tailed test, we know, I guess it was alpha was 0.05, right? That's right. So this should read 0.05 and not 0.01. You have made the decision rule that in order to reject the null hypothesis, I must be at least 95% confident that it is false. Another way of saying that, as it relates to this sampling distribution, is to say I will only reject the null hypothesis if the observed value of Z is somewhere up in this shaded region. That is greater than plus 1.65. And it ain't. It's somewhere down here. All scores in this lined region you would interpret as insufficient evidence to reject the null hypothesis. So you, in this example, you would once again fail to reject the null hypothesis. That is, you would conclude that there was no significant difference between the average income of males and females performing equivalent tasks in that particular organization. I suspect that if you had never seen anything of this process, you would have looked at the average income of the males, $30,500, and the average income of the females, $25,000, and you would have concluded and argued that this organization is sexist because males earn significantly more than females. You can't just look at mean scores. What you also need to be sensitive to is the amount of variance in those scores. That's obviously an inherent feature of hypothesis testing when conducting a z-test, because it's in the computation of the observed value of z, S1 squared and S2 squared, the variance of each of the groups. And it's the reason why in this instance we concluded that despite a $5,500 difference in the two mean scores, there was no significant difference between the average earnings of the two groups. The last part of that discussion is less important than the first part. This process, no matter how complex we get in our hypothesis testing this semester, is always a three-part process. One is determining the critical value of the test statistic, in this case z. And you need to then determine whether the test is one-tailed or two-tailed. And second, you need to know the level of alpha. The second part of the trick, it's not really a trick, the second part of the process is to compute using some formula that you'll be given, not on the exam. You're going to have to memorize these formulae. But you'll simply invoke some formula that will allow you to compute the observed value of the test statistic. And the third part of the process is the comparison of those two scores in such a way that it allows you to validly interpret or evaluate the null hypothesis. I would hope that by this point you get the first part of the process, that you can determine a critical value of z. I would hope, second, that you can compute an observed value of z, because all that requires is taking data that you've been given and putting them into a formula. I'm less concerned at this point if you still are uncertain about evaluating the null hypothesis, because we're going to be doing that from now until long after you've had grandchildren. By the second exam, you will be able to do this stuff in your sleep, or you won't be able to do it at all. There were some questions. Part 1. Are there any other questions?
This is just, as a way to remember it, dating back to like p-value. So since your alpha represents your critical value, just remember that rule. Just always remember that rule when your how's it go? When your p-value is less than alpha, you just reject, and when it's greater, you fail to reject. Right? That applies to the observed values. Okay.
Yeah, one could also say when the absolute value of the critical score exceeds the absolute value of the observed score, you fail to reject. Yes.
In the last example, we turned the observed value of Z into, like, we went to table A, but in this example, we didn't do that.
Yeah, because I'm introducing some ideas to you along the way that will be more important in the future than they are right now. This P and alpha thing will become much more important in the future because at some point we're going to get away from the computation. All we're going to be doing is interpretation. So I'm just introducing some of these ideas along the way. The critical issues here are a critical value, an observed value, and then interpreting the null hypothesis. In terms of the first part, that is determining a critical value of the test statistic, here's Z, you need to know whether the test is one or two-tailed. That determination is based on the research hypothesis. If the researcher predicts that two groups will simply be different to one another, then it's two-tailed. If the researcher predicts difference and direction, it's one-tailed. The second thing you need to know is the level of alpha. A researcher decides that. To do something I said I wouldn't do, on an exam, you will be given the level of alpha. You then have to go to Appendix A or Table A, but actually you don't have to go to Table A because in Z-test there are only 4 scores that ever come up. Alpha equal to 0.05, alpha equal to 0.01, number of tails 1, number of tails 2. You got a 2 by 2. You just put those values in that 2 by 2, you commit it to memory, and you're ready to go. Are there any other questions? Before next time, and I'll say something, let me just say that before next time, please read the pages of the chapter that deal with not Z-tests, but T-tests. T-testing is useful or appropriate when you're dealing with small samples. Okay? Okay. Don't go anywhere. I have something to say.